Let's get started. Hello, everyone. Welcome to the AI Virtual Tech Talk series, and thank you for joining us today from your home or office around the world. I'm Felix, and I'm part of Arm's machine learning engineering team based in Lund, Sweden. I work primarily with optimizing machine learning kernels and on the story around it for Cortex-M CPUs. I'll be the moderator for this session, and I hope that the next 60 minutes is worth your time. Next slide, please. There's a short lag between. Great. This is the running schedule for the AI Virtual Tech Talk series. The theme for this round is tinyML and is delivered by Arm together with its leading AI partners. Today, we talk about how Arm supports Tensorflow Lite Micro for its Cortex-M CPUs and Ethos-U NPUs. After this round ends in August, we plan to continue this series with more new topics and virtual workshops. Please visit the link below that you see to register and to keep track of the talks. Next slide, please. It's now time to introduce you to the lead speaker for this session, Fredrik Knutsson. Fredrik and I go way back, and we work together in different companies and departments over the years. This is actually the first time that we are doing such a joint presentation, and I'm looking forward to it. Over to you, Fredrik, for an introduction.
Thank you, Felix. So my name is Fredrik Knutsson. I work as a software team lead in the machine learning engineering group in Lund, southern Sweden. So same office as Felix. So we spent the last year or so working on the software related to Ethos-U55 and our Cortex-M processors. So my background is mostly within telecom, but I also have a few years of experience in the automotive business and also the wearable business. So I'm looking forward to hold this presentation to you, and I hope and think you will find it's worth its time.
Thanks, Fredrik. I see the count of attendees increasing. And while we wait a couple of more minutes, let's get to know Fredrik better. Fredrik, I know Sweden celebrated Midsummer a few days back. In the world of physical distancing, how was it compared to previous years?
The Midsummer it's a strong Swedish tradition, and usually it's celebrated with friends and family. But of course, this year with the COVID situation, it's a little bit different. However, we managed to celebrate with a bunch of friends, and we checked off the traditional Swedish midsummer traditions, such as pickled herring, drinking schnapps, and singing songs. And actually, I have a question for you, Felix.
Yeah, go ahead.
So Felix is a great photographer. Especially, he is good at photographing at the concert. So tell us, what's your best memory from photographing concerts?
Well, I've been fortunate enough to get a foot into the concert photography scene, and I usually photograph around 100 performances a year. Among those, my absolute favorite would be of Florence and the Machine from Way Out West Festival in Sweden a few years back. It was one such case where I entered the photo pit with zero expectations, and as I had never seen her perform before, and was treated to an exceptional and passionate show from an artist who knows how to own the scene. It's still a goosebumpy memory for me.
Cool.
Now, speaking of passions, I know you're into lobster fishing. How does one even get into lobster fishing?
That's a good question. So I grew up on the Swedish west coast in a small town called Hunnebostrand. It's a beautiful place, and there just happen to be a lot of lobster there. So as long as I can remember, from I think 4 years of age, I've been fishing pretty much every year, and still today I take 1 week of vacation each year to go fishing for lobsters.
Great. Let's wrap this up with one final unfair and a tough question to Fredrik. So all you have to do is pick one of the two choices that I give you.
All right, shoot.
Ready for it?
Yeah.
Liverpool FC or lobster fishing?
Oh man, that's a tough question. I guess I have to say Liverpool FC now, because they managed to win their first trophy in the Premiership in 30 years, just last week.
Fair enough.
Liverpool.
Great. Well, on that, now that you have had the tough question, like on the bright side, you will find the questions that we're about to get to be much simpler.
Okay, good.
So please raise your questions using the Q&A button as and when you have them, and we'll take them during the course of this presentation itself. Over to you, Fredrik.
All right. Are we ready to start?
Next slide, please.
Okay, it's a little bit like that. There we go. Okay. So there's 5 bullets on the agenda today. And first, I will start off by talking about Tensorflow Lite for microcontrollers. I will continue to talk about CMSIS-NN, CMSIS for neural networks. And I will continue to talk about Ethos-U55, Arm's new class of machine learning processor. And then I will talk about how these 3 components integrate together. And I will finish off with a demo that shows the performance uplift with CMSIS-NN using Tensorflow Lite on an Arduino. So I think it's a great demo, and I don't think you want to miss it. So stick around. So we can do the next slide now. Let me see, there we go. So we start talking about the Tensorflow Lite micro. We can go to the next one immediately, I think. There we go. So Tensorflow Lite for microcontrollers, or TFLu, or Tensorflow Lite Micro, as we call it. It's a version of Tensorflow Lite that executes on memory, MIPS, and energy constraint systems. So it's designed to be portable even to bare metal system that has no heap implementation or no OS. So it has to be quite small, and currently it has a runtime of only about 20 kilobytes, and it's scalable on top of that. So if you have an application that only uses a model that has 5 kernels, only these 5 kernels will be compiled into the final binary. And the repo contains a few examples and demos related to voice, video, and vibration. So if we start with voice, we have an example or a demo called microspeech. It's an application that will detect simple commands such as yes and no. Then we have on the video, we have image recognition that detects objects in an image. And we have person detect that we will look, this is the demo that we'll show later. So that will tell you whether there is a person or not in an image. And then there's also a vibration demo, which is called Magic Wand, which uses an accelerometer data to detect gestures. And it's TensorFlow Lite Micro is integrated to several different projects. So you can generate, for example, embed OS projects. You can generate, as we'll see, Arduino projects. And right now it supports more than 50 operators. All of the operators supporting multiple data types. And some of the operators have accelerated hardware support for multiple different hardware. A couple of examples is the DSP instructions that are available on Cortex-M4, 7, and 33, and MV extensions that is available on our new Cortex-M55. Okay, next slide.
Let's take a question here, Fredrik. So the question is, I have a requirement for people counting using camera both indoor and outdoor. What is the best Arm MCU camera and open source project to do that?
Ooh, that's a really tough question. I might not be sure how to answer that, but the DSP-enabled processors that we have on the market, M4, M7, and M33 should be good options.
Good options, yeah, absolutely. And I guess like using the demo that you show at the end would be a very good starting point for this kind of application. So great, thanks.
All right, that brings us to CMSIS-NN, which provide optimized kernels for Cortex-M CPUs. Which are available on TensorFlow Lite Micro. So, but before we start talking about CMSIS-NN, let's talk about CMSIS. What is that? So, CMSIS stands for Cortex Microcontrollers Software Interface Standard, and it's a collection of APIs and utilities, methods that will help you accelerate your development of microcontroller applications. So you can use, for example, as a software programmer, you can utilize an RTOS. There are optimized DSP functions. There are debug capabilities, etc. And CMSIS is open source. It's hosted by Arm and is available on GitHub under a Apache 2.0 license. So it's quite easy to use and to build upon. So now let's see how CMSIS comes into this ecosystem. If we move to the next slide. There we go. So here's an overview of what I just mentioned. There are many software components under the CMSIS umbrella, and CMSIS-NN is one of them. CMSIS-NN provides optimizations for Cortex-M CPUs, and the preferred entry point to use these optimized kernels is TensorFlow Lite Micro, and we will talk more about that in the integration section later on. So there are optimized kernels for DSP-enabled Cortex-M CPUs and MV-enabled Cortex-M CPUs, such as the Cortex-M55. So let's take a deeper look into CMSIS-NN. Can do next slide. There we go. Okay. CMSIS-NN involves some different optimization techniques, and I've only one slide to summarize this, so I will focus on the largest contributor of the CMSIS-NN performance optimizations, and that is SIMD instructions. SIMD stands for single instruction on multiple data. And one such SIMD instruction is MAC, which is multiply and accumulate. And neural networks involves a lot of MACs. So basically, you can do a multiply and accumulate in one cycle instead of multiple. You can even do multiple MACs in one cycle, as we will see. And there are two categories of SIMD support, DSP extension and M-profile vector extensions. So let's start with the DSP extension. It is supported, like we mentioned before, on our Cortex M4 and M7 and M33 CPUs. Cortex M4 supports 1 MAC per cycle. Cortex M7 supports 2 MACs per cycle because it has dual issue pipeline support. If we move over to the M-profile vector extensions, or as it is also known as Helium technology, our new IP Cortex M55 CPU supports this technology, and it enables you to get up to 8 MACs per cycle. So the figure below in this slide will illustrate the principle of the vector extension. So it utilizes 128-bit wide vector registers. So we populate 2 of these registers with 16 operands. In this illustration, it's denoted A1 through A16 and B1 to B16. So these will basically be multiplied and accumulated in 2 cycles. So 16 multiplication in 2 cycles, there we have the number 8 MACs per cycle. And that's the essence of the optimizations. So we can go to the next slide. So we see in the technology, and this slide shows a couple of examples of what performance you can expect when using CMSIS-NN with the Cortex M55 CPU. And it shows the performance of some popular neural networks versus Tensorflow Lite micro reference kernels. So as we can see, we get about 10 times the performance on MobileNet V2 and 11 times the performance on WAV2Letter. Of course, these numbers depends on a lot of things. It's measured for us, it's measured on the FPGA reference system. But things that matters a lot are, for example, memory access latency, cache performance, compiler optimization, etc. But at least this gives you a ballpark number. And more importantly, this is for free, basically. We just utilize the CPU in a better way. So we will continuously improve the performance of computationally heavy kernels. We will talk about that a little bit more later, but for non-computationally heavy, we rely on falling back to Tensorflow Lite micro reference kernels. More about that later. Okay, I think we'll go to the next slide here. But before we go on to the next section, maybe have you got any questions, Felix?
There have been a bunch of questions, and I thought we'd take this one online as it is very relevant to the tinyML scenario. The question is, how much can we perform on edge devices? And can we use embedded edge devices to detect if a person is wearing a mask or not? And is that intense application possible now?
Good question. We will see a person detection demo later where we, it's a little bit simpler use case, I guess, because there's either person or not a person, not a mask on or mask off. But yeah, it's a hard question to answer, but I believe what we will see later on in this presentation with Ethos-U55 is that we can do a lot more advanced models and thereby much more advanced detection patterns.
Yeah, exactly. And to add on to that, like when you talk about a model like person detect, we are talking something in the ballpark of like 5 or 6 million max for a network. And that is quite doable in a Cortex-M CPU with the DSP extension or Helium technology for an embedded application. So absolutely, yes.
Do we have any more questions?
There's one on which is more related to quantization in a way. The question is fixed point inference the way forward for MCUs? So do we see the need that there would be a coexistence with floating point inference?
For the computationally heavy kernels, I see fixed points at the future, but there may be, it's definitely possible to do less computationally heavy kernels in floating point.
The direction I believe that we are going ahead with quantization, especially with int8 and symmetric quantization, is that we're moving from a floating point to 8-bit fixed point representations.
Makes sense. Good question.
All right. Let's go ahead, Fredrik.
Yep, next slide. So now I will talk about the Ethos-U55. And what is that? It is a neural network processor or micro NPU for Cortex-M systems. It works well alongside many different Cortex-Ms, such as M55, M7, M4, and M33. And it's designed for just that. So it's designed for embedded type of system where you typically have a fast on-chip SRAM and a slower system flash. Its computational power enables us to dispatch heavy compute operators onto this piece of hardware for faster execution. It also enables weight compression to reduce the memory footprint. The Ethos-U55 IP comes configurable in 32, 64, 128, or 256 max per clock cycle. So there's a comparison to the slide where we talked about 1, 2, or 8 max for the Cortex-M CPUs. Okay, can go to the next slide. Okay, so the hardware comes with a software flow. For an end user, it can look something like this. So if we start with the left gray box, and we will go through the arrows 1 through 5. So typically, when you develop an application, you train a network using TensorFlow. And via arrow number 1, you quantize it into a flat buffer, TF-Lite file. That flat buffer file we feed into an optimizer that we call the Vela compiler. And the Vela compiler will identify what to run on Ethos-U55 and how to run it. The output is a new TF-Lite file. This TF-Lite file is now deployed using an app on the left side of the figure, so on the left gray box, which is the target. And it can be the TensorFlow Lite micro runtime will, by using the TF-Lite file, discover what will be should be dispatched to the Ethos-U55 micro NPU, what can be dispatched to the CMSIS-NN optimized kernels, and if none of that is available, it will dispatch it to reference kernels. All right, I think we can move on to next slide, which is the Vela compiler. I want to talk more about that because it's a vital part of this software flow. So it's a Python-based tool, an optimizer that executes on your computer. And in principle, like I mentioned before, it reads in a TF-Lite file and modifies it and writes out another TF-Lite file. So one example we can see in the figure here, where in our hypothetical networks we have some operators. In this picture, it's other, conv, pool, fully connected, and then another op. So let's say we can dispatch the convolution, pool, and fully connected to the Ethos-U55. So the Vela compiler will read this TF-Lite file. It will convert and these three operators into a custom operator. This custom operator will contain instructions or a command stream for the Ethos-U55 hardware to consume. And the conversion process is not only converting into hardware instructions, it also involves some significant optimization techniques. And one is fusing of operators. Another is cascading of multiple layers in order to reduce the SRAM footprint. It balances available bandwidth with the micro NPU compute. It can prefetch model parameters from flash into a faster memory. And it, like I mentioned before, it can utilize weight compression in order to reduce the flash footprint. And this tool is open sourced since a few weeks back. There will be links available towards the end of this presentation to find that. All right, next slide. Okay, we see the flow. We talked about the hardware. We talked about the Vela compiler. So what if you put this together, what kind of performance do we get? And as you can see in this slide, we get quite a significant performance uplift. This basically enables you to execute networks that previously hasn't been able to run on a microcontroller. Same networks as we talked about before, Web2Letter and MobileNet V2. And the numbers here are compared to Cortex-M4 on the similar FPGA reference systems with CMSIS-NN optimizations. So about 280 and 300 times the performance respectively. All right, I think we can go to next slide and we take a short break for questions. Felix.
Great. Now we're almost midway through the session and you have a fair idea of what you're going to gain from this session. With that in mind, we would like to know what topics you would like to hear from us next. So we're going to start a poll with a few topics in mind, and your input there would be highly appreciated. All right, and maybe I can take a couple of questions here, Fredrik. So the question is, does Vela compiler work for only M55 or U55 and M55?
The Vela, what combination?
It was M55
and micro NPU doesn't matter. It works for, it supports other Cortex-M CPUs as well.
All right. And so another scheduling question. So when will the first Cortex A55, I believe it's actually about M55, I believe, be available for developers and researchers?
M-Core plus Ethos-U55 sometime next year, I believe.
Great. This is a slightly tricky one. As the ML technology is advancing quickly, how can you be sure that Ethos-U55 architecture will continue to be relevant by the time it is widely available?
That's a really good question. And one really strong side of the Ethos-U55, as we will see in the next session, is that we always have the possibility to fall back into executing reference kernels. So as soon as something becomes available on Tensorflow Lite Micro, it is supported by our software flow as well. And then we can continuously optimize or gradually optimize things into CMSIS-NN and Ethos-U55.
And on top of that, I believe there is a very wide list of operators that Ethos-U55 already supports. So,
absolutely.
Great, thanks. All right.
It's a good. I like this. I like this poll. Looks like the virtual workshop is high on the list.
Great. Let's continue.
All right. Before we start the next section, I would like to say as well that both CMSIS-NN and Ethos-U55 is bit exact to Tensorflow Lite Micro kernels. So you can expect the same inference accuracy as reference kernels. Okay, next slide. Okay, as we can see from this block diagram, your application interfaces towards the Tensorflow Lite Micro runtime, or the micro interpreter object of the Tensorflow Lite Micro runtime. To be more specific, Tensorflow Lite then interfaces to CMSIS-NN optimized kernels or Ethos-U55 driver, depending on where the operator is going to be executed. And to be exact here, actually the driver and the kernels are compiled into the Tensorflow Lite lib, which is then linked into the application for when you create your final binary. Now this is realized using something called tags in the build system. We will see an example of that later. All software on this slide, the Tensorflow Lite Micro runtime, CMSIS-NN optimized kernels, Ethos-U55 driver, and also the Vela compiler we talked about before is open source. Links will be available in the end of the slide deck. Next slide. Okay. We have designed the software for functionality, and we focus optimization on the kernels that stand for the significant amount of compute. Then we always want to have the possibility to fall back into reference kernels, so we can accelerate execution further on CMSIS-NN for more horsepower and Ethos-U55 for even more horsepower. So this will enable us to always be able to run a network that is supported by Tensorflow Lite Micro, and try to illustrate that with a table to the right. So here we have some hypothetical kernels 1 through 7. Kernel 1 to 4 is supported by TFLu reference implementation, CMSIS-NN and NPU in this example. Kernel 5 is supported by Tensorflow Lite micro reference implementation and CMSIS-NN, and 6 and 7 only by Tensorflow Lite micro reference implementation. So this gives us a good way to always support a network that is supported by Tensorflow Lite micro, basically. So if there is, let's say there is a new kernel, new operator coming into play, as soon as it's supported by TFLu, we support it, and then it can be gradually, like coming back to the question we had just before, we can gradually optimize that kernel to executing or on Ethos-U55 or via CMSIS-NN. Okay, next slide. So here's an example of how this works. So all you need to do is to clone, first clone the TensorFlow repo, and then you build using tags equal to Ethos-U and CMSIS-NN, and that will enable your optimizations. And target, you have to have a target specification for a piece of hardware that supports Ethos-U55. So I don't want to confuse anyone now, because like we got one of the questions, Ethos-U55 will be available on the market next year. But this is how you would create the Tensorflow Lite micro integration. And if we follow that long step to make line, the last thing that we will see is person detection int 8, and that is the recipe you're building. In this case, it is the person detection demo that we will see later on. So Ethos-U55 is not on the market yet, but one thing that is on the market is our Cortex M4 CPU. And that brings us to the demo. All right, Felix, do we have any more questions on the previous section?
All right, I was on mute. So there have been quite a lot of questions that are answered already. So if you're attending, and please have a look in the answered questions as well, just to see if it answers any questions that you're interested in. And I can take this question. This is an interesting one. Would TVM change this flow in terms of, I guess this is a reference to Vela.
It's a good question. So the Vela compiler takes a network and makes it executable on the Ethos-U55 backend. So you may well, and we're definitely looking into this, apply this flow on TVM, because TVM is more of a network modifier, if that makes sense. I hope, TensorFlow and TVM could be compared in this use case, and the Vela compiler will basically translate this into a backend compute.
Exactly. So it would still, the Vela compiler would still be relevant in the case of TVM, as TVM would still utilize the output of the Vela compiler to create its executable. So absolutely, it would not change the flow, except that you wouldn't have, you probably wouldn't have TFLu as the runtime there. All right. So you would now like to prepare for the demo, right, Fredrik?
Yes. So in this demo, we will see what CMSIS-NN can do in terms of performance uplift in an embedded use case on an Arduino hardware. So if we move to the next slide. There we go. So there's a picture of what I have here. It's the Arduino Nano 33 BLE Sense plus an ArduCam. And this chip, this piece of hardware is powered by Arm's Cortex-M4 CPU. It has a megabyte of flash, 256 kilobytes of SRAM, and 64. It's clocked at 64 megahertz. So you can find the full instructions how to connect these wires and more in the README MD file, the markdown file in the TensorFlow repo. A link will be available after this presentation as well. So first, a big thank you to Pete Warden and Google's TensorFlow Lite micro team for being a huge help in putting this together. I would also like to thank the Arduino team for their swift release. So TensorFlow Lite is available as a library in Arduino, and the latest version of that library now also includes CMSIS-NN and optimized kernels. So even though this demo is done with Arduino, there are many other targets available on the TensorFlow repo. You can find, for example, a SparkFun board. You have a few boards from ST Microelectronics available. And since I mentioned briefly in the beginning of the presentation that you can generate projects, so you can generate an embed OS project. And by doing so, it enables target configurations for hundreds of boards. So have a look at that. Now we can go to the next. All right, here's a step-by-step instructions. First, clone the TensorFlow repo from GitHub, and then you generate an Arduino project. These two steps might take a while, so I've actually prepared two versions of it, one with CMSIS and one without CMSIS. Step 3, you unzip these the generated project into your Arduino libraries folder. Now, then you go to step 4, and you can compile and flash this demo using the Arduino IDE. Now, this is, like I mentioned before, it's integrated into the TensorFlow that exists in the Arduino IDE. So it's actually only a one-click to install this package. If you choose the latest version, you will get the CMSIS-NN optimizations. Okay, so I have prepared a build without CMSIS, so we will look at that first. So I'm gonna take over the screen. Let's see. Can you see my screen, Felix?
Yes, I can see it.
Let's move this. All right. So we'll just connect the board to my USB. I hope the demo guys are with us today. Let's see what happens here. So I've connected the board to my computer, to my laptop. I've enhanced or increased the font size here, so you all can see, read what I'm doing here. So first, I just want to take a look at the serial monitor here, what comes out. So I expect some output for each, when each inference is done. And without CMSIS, it takes, here we go, and here's some extra prints that I've added. So as we can see in this case, it takes about 19 seconds to finish an inference. And yeah, here we go. So I'd like to show this on the board as well, because they've done it quite nicely using a LED. So I'm going to stop sharing. here. And if we can focus on mine camera, there we go. All right, so look at this. It has the LED blinks in 3 colors, or has 3 colors: blue, red, and green. Blue means it captures an image. Red means no person, and green means a person. So maybe you didn't see that, but it just turned over to green, and before it did that, it captured another image. The first image was probably captured on me. Now I'm focusing this camera right into the wall. So I expect it to be red, and there we go. So now it has already captured a picture of the wall, so it's gonna be hopefully red next time as well. But if we wait another, let's see, here we go. That was another capture, and a red because the previous picture was on the wall, and now I expect it to be green because it's facing me. There we go. So that's how the demo works, and as you saw from the printouts, it takes about 19 seconds to do the inference. Now I've prepared the build here for the same demo, but using CMSIS-NN. So we're gonna see what type of speed up we get. So I do compile here. This is gonna take a while. So if you wanna
we could
entertain the crowd.
Absolutely. We could take a question in the meanwhile. So I can take this question. What is the Vela compiler equivalent for M4, M7, and M33? So it's nice that you make that comparison, but to me, the equivalent would be quantization, for example, wherein you convert a floating point model into a int8 model. That in itself optimizes your model both for speed and size. And on top of that, you could apply pruning or any other optimization technique that you apply on the network in itself. That you could say is roughly the equivalent. And the end result would still be a TensorFlow Lite model, right? So there's one more question. Why do we compare CMSIS-NN and U55? One is software and the other is hardware. You have a valid point there. When we usually compare CMSIS-NN and Ethos-U55, what we are essentially trying to do is we are comparing a Cortex-M, the performance of a Cortex-M CPU with the Ethos-U NPU. And in a way, we synonymously use CMSIS-NN to represent the performance of a Cortex-M CPU. That is why you see the usage.
It's a good question. All right, still compiling here. Maybe we,
I think it's pretty close.
Yeah, it should be pretty close now. There we go. And it's gonna flash the board in a few seconds, I believe. There we go. Flashing starts. Okay, flashing is done. So we do the same thing here. We open the serial monitor to see the printouts. As you can see now, the text goes by a lot faster. So we stop the scrolling there. We can see here 1.2 seconds. So instead of 19 seconds, 1.2 seconds, which is quite a significant uplift, what's that, 16 times the performance or something like that. All right, so let's look at the LED. All right, if we can get focus on my video here again. There we go. You can see that it's going to flicker by a lot faster. Now, as I said before, it's the CMSIS-NN implementation is bit exact, so we don't expect any accuracy difference, but I'm just going to prove my case here. So we moved towards me, and oh, typical demo bad luck.
I think it's frozen.
I've been bending these cables for the past few days. So there we go. Start over. Okay. Well, it doesn't like my. Fix this. If it just worked, it wouldn't be any fun, would it?
Absolutely.
Okay. Do we have any more questions, Felix?
Absolutely. I can take a few more questions. Yeah. And thanks a lot for coming up for all these questions. Really appreciate it. So let's see if we can take this one on CMSIS-NN. Will CMSIS-NN support floating point in future and make use of FPU if available? Right now, I would say no. And going by the direction of how quantization, going by the direction that quantization is taking on, I'd be very surprised that if we move towards floating point models in future. So not at the moment. Let's see if we can get some more questions.
All right, I think I have it up and running. I'm not going to bend these cables too much. So can you see the lights flickering there? That's zooming on my, so there we go. We have, looks like it's detecting me as a person. So if I flip this towards the wall like this. All right, here we go, no person, no person.
It's a much faster frequency to the blue light.
Yeah. There we go. I'm bending it carefully now. Into the wall. No person against me. Person. All right. Got it working.
Great.
So, yep. We can go on with the slide set, I think. If we can focus back on the slides. There we go, and we can go to the next one. Okay, so we've seen the demo, and here are some links that you may find useful. First one is Tensorflow Lite Micro plus CMSIS integration. Next one is similar, but for Ethos-U55 instructions. We have a link to the CMSIS-NN GitHub project and the person detection int8 example that we just saw. We have Arm AI landing point, good, lots of interesting reading on that link. And finally, you have the ML platform Ethos-U55 landing page. So there you will, on this link, you will find other links to the Ethos-U55 driver, the Vela compiler, etc. So have a look at that. We can go to the next slide. Go to the next slide. It's a little bit of lag here in the IT. Okay. Can we try? Perhaps Merrick or can try to share. It's only the last slide. So basically, we're a team here in Lund, Sweden. A big team that has helped out in realizing this demo, presentation, and optimizations, etc. And if we get the slide up here, we can see some of the names that you may recognize from Tensorflow Lite Micro and CMSIS-NN contributions. There's, of course, a lot of people involved in this. So there we go. There are the names, the GitHub IDs. So don't hesitate to contact us. And I hope that you enjoy this session. And I want to thank you for listening. So we will stay on the line for a few more minutes. So if you have more questions, please post them. I think you're on mute.
All right, yeah. Thanks, Fredrik, and thanks everyone for joining us today. As Fredrik said, we'll stay a while longer to answer your questions. So, and if you want to ask your questions live, please stay back. And if not, we'll hear from you in 2 weeks' time when we have our next session with one of our leading AI partners, Cartesium AI. Thank you.
Thank you.
So let's see if we can take a few more questions, Fredrik.
Yep, absolutely.
So there's a question on CMSIS-NN. Can we train the model on controller itself using CMSIS-NN? Now, I can take that question. So that is a completely different topic, and like there are quite a lot of research and advancement going in there, wherein like you want to train your network on the edge device in itself. And I'm sure it's quite likely that in future we would see that. And when that happens, absolutely you would want the best performance for your device, and CMSIS-NN would be very relevant in that case. A question for you, Fredrik. Are you hiring for the team?
That's a good question. I have to get back on that.
All right. If you have any more questions, please just go ahead. Maybe I can take one more. So the difference between the two instances is the recompiling of the application using Vela. I'm assuming it's a continuation of a previous question on like how work using Vela is different from using a network as it is with TensorFlow. Did you get the question?
No, can you repeat the question?
So the difference between two instances is the recompiling of the application using Vela. I'm a little bit hazy on what preceded the question, but Vela is an offline tool. So what you would be doing is like you would, as an offline thing, like you would take your network and then pass it through the Vela compiler and generate a new TFLu file, and then use that in your application.
Yeah, okay. I see the question.
Yeah.
Exactly. So the flow is basically you take, once Vela has outputted a TFLu file, you turn that's a binary blob. So you use any kind of serialization tool, like in Linux, there's something called XXD, and you make that into a hex dump, ASCII hex dump, basically, and then you include that in a C file in a global variable as your model. And that variable you feed into the model parser that is available from TensorFlow Lite Micro, and that will be able to interpret it as as a model.
Great. And let's take one more on the power efficiency of Ethos-U55. The question is, how does the power efficiency of Ethos-U55 compare to running the same model on M55 and M4?
It's a very hard question to answer because it depends on how it's built. So Ethos-U55 is an IP.
Right. And I guess like since we are talking about the speed up of like many hundred times, we are keeping the processor and the NPU alive for a shorter amount of time. And so you would get your power efficiency through that as well.
Exactly.
Yep.
So it has, the question is really a good question. And it has many dimensions. There's a lot of dimensions to that question.
Great. So that, I think, more or less covers the questions. If there isn't anything more, then we'll end the session here. Thanks again, everyone, for joining us today, and hope to see you in the next presentation. Thank you.
Thanks. Bye-bye.